Yesterday I finished with this question where we're doing the confidence level at, what do we do, 90%. What I'd like to do is take a moment and just real quickly see what happens when we want to increase our level of confidence. So we'll run through these values here again in a little bit, but let's go ahead and do this confidence level at 95%. So when our confidence level equals 95%, that means our alpha is 0.05, and then alpha over 2 would be 0.025. So in your table, if you're using your z table, you'd be looking for either that value, okay, as an area, and then align that with the z-score in the left-hand column and the z-score in the top row. Or you can look at the 9 or 0.975, sorry, 0.9, yeah, that's right, 0.975. You can look at that area as well to find a z-score. So if I'm looking at 0.975, if I've got this going out far and I don't have it going far enough, let's get a z-table up. So if I look at 0.975 here in the z-table, go over to this column, 1.9, intersect that with the row of 0.06. So we're looking at our z sub alpha over 2, and this one would be the one to the right of the mean, to be positive 1.96. The other one would be negative 1.96. And that's what was being stated here yesterday. But if we want to find then the confidence interval for 95%, we're going to say x bar, it'll be minus z sub alpha over 2 times then my standard deviation of the sample means is that. That's going to be less than mu is less than x bar plus z sub alpha over 2 times my sample means, or standard deviation of my sample means. So now we said the best point estimate was this 19 minus 1.96. Sigma, we said in the problem was 6.8, and we were looking at 50 people. Less than mu, less than 19 plus 1.96 times 6.8 over root 50. And that should give us a interval as well. So just grabbing Desmos here. We did, so when we were doing the 90% confidence interval, that would have been the 19 minus 1.64 times the square root, or times 6.8 divided by the square root of 50. So that would be the lower bound. If I go 19 plus that, okay, that gives you my upper bound. So that was yesterday, so 17.42 and 20.57. So this was 17.42, 20.57. All right, so the calculation we just did then would be essentially, if this turns into 1.96, And this becomes 1.96. So now we're looking at 17.12. 17.12 less than mu less than 20.88. And then if we go 99 percentile, so 99 percentile, the only thing that changes is the um, z sub alpha over 2. That turns into 2.58. 2.58. And you're going to be asked occasionally to do multiple confidence levels, so it does make sense to use some type of technology, some type of software that allows you to change those values quickly. You got to run through everything, type everything in again. So 16.52. 16.52 is less than mu is less than, oh, my daughter's picture. 21.48. 21.48. Okay, so remember this was 90 percentile or 90% confidence level. This was 95%, and this one here is 99%, and that's what we were talking about 2 days ago. Was that when your confidence level increases, okay, what's going to have to happen is that your interval, your confidence interval, widens. Okay, so as your confidence level increases, your interval widens, and that's to be. Yeah, hopefully, it makes more sense. That I think I used in one of the classes. I used the idea that if we think about like kicking field goals, okay, if I'm kicking field goals through these two goalposts, I'm not going to be that confident. Okay, but as the goalposts widen, kind of like these intervals widen, my confidence is going to increase on my ability to make a field goal. Okay. So the next question says, suppose average pizza delivery times are normally distributed with an unknown population mean and a population standard deviation of 6 minutes. A random sample of 28 pizza delivery restaurants is taken and has sample mean delivery times of 36 minutes. Find the 90, 95, and 99% confidence intervals. So in this problem, the best point estimate is the sample mean delivery time. It's the 36 minutes. So X bar is 36 minutes. Okay. Sigma, the standard deviation, is 6 minutes. Okay. And we want to be 90% confident. Okay, so 90%, remember that yields to 1.64. Z sub alpha over 2 is essentially a Z score. 95%, we want to get to that. That's going to be the 1.96. And then the 99% is going to be the 2.58. So I'm just going to write the formula here for doing it for 90%, and then we will go to technology and get the other two pretty quick from that. So again, we go X bar minus Z sub alpha over 2 times that, less than mu, and then it's the same thing, but we go plus Z sub alpha over 2. So plugging that stuff in, so X bar was 36, minus 1.64. Okay, standard deviation, 6 minutes. And the square root of n, so we had 28. Okay, so maybe that should have been another value we put over here. N is 28. Less than mu is less than now. 28's not, it doesn't hit the 30 object threshold for the central limit theorem. But if you read the first line, it says that they are normally distributed, so that number can be anything then. If we didn't know whether it was normally distributed, that number would have to be greater than or equal to 30. All right, so I think it makes sense maybe if we should be able to program Desmos we can say x minus z, and then we'll go just times sigma divided by square root of n. And what I like about doing this is it'll just make things a little bit easier to adjust. So make that plus. So now all I have to do is define our value. So x we said was 36 minutes. I don't know if I can put in Desmos these things all together at once. X was 36. Let's say z was 1.64. S was 6 and n was 28. Yeah, it doesn't let me. So we just have to put them in their own lines. There are some programs that will let you put them all in the same line with one another. All right, so we see that with 90% confidence, our mean, our population mean, will be between 34.14 minutes and 37.86 minutes. If we want then a 95% confidence level, all we have to do, and this is why I like writing it this way, all I've got to come through here and change that to a 1.96. And you see that these two automatically adjust then. Okay, so now we're looking at a 33.78 minute to 38.22 minute interval. So that interval has widened now. And if we go then 2.58, it gets even wider. 33.07 minutes to 38.93 minutes. And remember what that means. We are 99% confident that the population mean that we do not know is going to be between these two values. Another way of thinking about it is that if we were to repeat this sample over and over and over and over and over again and actually find their means, then their mean will occur in that sample to be between these two numbers 99% of the time. So all those key concepts down here at the end of the notes was talking about says what do you notice about increasing the confidence level does to the interval. We already talked about that. As you increase the confidence level, the interval widens. Here it says compute the 95% confidence level of the pizza delivery question using n equals 20, then n equals 40. If n equals 20, n equals 40, so then really all that's changing in our formula, so we would have 95%, so we had 36 as x bar, we're going minus, it's 1.96, sigma is 6 over root, we did root 28, less than mu, less than 36 plus 1.96, 6 over root 28. So let me just take a real quick look at what those values were. So when this was 1.96, we have that interval of 33.78 less than mu less than 38.22. Okay, so it was n equals 20. If we go n equaling 20, and I'm going to actually do it above here. So we'll go 36 minus 1.96, 6 divided by root 20. Okay, you kind of think about what happens here. It's a smaller denominator. Okay, so this product is going to be, this product here will be larger than what it was there. Okay, so now all I'm going to do is come down here. We're going to change this 28 to 20 and come back up and see what that does. So now this gives me 33.37 less than mu less than 38.63. And then if we look at n being 40, so it'll be 36 minus 1.96, 6 divided by root 40. So now this number is smaller than it was here or there. So when I multiply it by 1.96, that product is going to be smaller. So this difference here should be greater than 33.78. We'll do the same thing on the right hand side. So 36.1 plus 1.96 times 6 over root 40. So again, in this program, all we do is change the 40. We see that this difference right there is greater than the 33.78, so 34.14 less than mu, less than 37.86. So it says, what do we realize here? Well, look at the pattern here. Okay, if n is 20, right now we're looking at. Let's see if we can kind of visualize this on. Something like this. Should be alright. So I'm just saying mu, I'm just going to call mu x just so I can kind of demonstrate this in GeoGebra. If I go 33.7 or 37 is less than x is less than 38.63. Okay, we end up with that interval. Okay. Then when we increase to 28 objects in our sample, we go to 33.78 less than x less than 38.22. So there you see, change the color here, change it to red. You see there that the interval got narrower by choosing a larger sample. We have a narrower interval. We'll talk about why that should make sense in a minute. And then using 40, we get that most inner bluish purple interval. And think about it. I mean, the more participants that I have in my average, the more reliable that average is going to be. Okay, so if we can ultimately increase our sample size, okay, increasing our sample size allows us to narrow our interval which then in like medical research and things like that, when we really want to have real high confidence intervals, and like very, I guess, yeah, confidence level, very high confidence levels, and we want really narrow confidence intervals, we want to focus on trying to get as many samples that we can, a larger sample size as we can. Hopefully this allows you to finish up that section 8.1 assignment, and we'll move on from here next time.